Okay, let's start with this example question to do with vertical circular motion. So we again have that situation of vertical circular motion of a particle attached to a thread. This time what is happening is that when the particle is at the highest point, let's say it has a velocity v1, okay, and the tension in the string is T1. Whereas when the particle is at the lowest point, tension is T0 and the velocity of the particle is V0. Okay. Now the length of this thread is given to us as 5 meters, and T1 is to T0 is equal to 1:7. Okay. So if the mass of the particle is equal to 1 kilogram, G is equal to 10 meters per second square. Find V0 and V1 and T0 and just try this out, people. Very simple question, but an example of a typical type of question involving application of vertical circular motion concept. Okay, so let's see the necessary equations first. Okay. So one thing you'll need here is the work energy relation, okay, between V0 and V1. So you can see that V1 square will be equal to V0 square minus 4GL.
Yes, sir.
That's from work energy. Okay. And then you have T1 is equal to mv1 square by L minus mg, and T2 is equal to T0 is equal to mv0 square divided by L plus mg. Okay. So the ratio of these two things is V1 square minus GL upon V0 square plus GL. And that is equal to 1:7. That you can take as your second equation. So using these two equations, you can find V0 square and V1 square in terms of GL. And then you can substitute the value of L and G, and you can find out the individual values, and from that you can find T1 and T2.
Yes, sir. So I've got it actually, but it's a tough job to type it in the chat.
Tough job to
Type it in the chat.
Oh, okay. Okay. It's coming as a square root quantity, that's why.
Sir, it's root 300, the other is 10.
Okay. So from the second equation, you can see that 7v1 square, okay, is equal to v0 square plus 8gl, correct? From this equation. So now substitute this here.
Yes, sir.
Okay.
Sir, root 2 GL, sir.
Oh, sorry. So root 2 and root 6, right?
Hi, sir.
This is becoming 10 meters per second. And accordingly, P1 will become mg and T0 will become 7 mg. Okay, so this is a standard format type of question, nothing very difficult. It's very good, Siddharth. Okay. So this equation is coming from conservation of energy. And these are coming from centripetal force concept. Okay, so I think this question is done. Let's move on to the next one.
Yes, sir.
Okay, now we'll look at an example involving. So first we'll discuss actually that if we have a situation where instead of a light thread, we have a light rigid rod, but of length L and vertical circular motion, then critical condition for completion of vertical circular motion and all that changes. Okay. So vertical circular motion of a particle attached.
Sir, I think we have done this.
Okay, so we know that 4GL, root 4GL condition, right?
Yes, sir.
Yes, sir.
Okay, okay. So here, if this is a rod, but it's light of length L, then the difference is that at the top, the tension can be upwards. So the condition for completion of vertical circular motion is that V should be greater than equal to Z. Okay. Actually greater than 0, we can say. Okay. So therefore, V naught should be greater than root 4GL. Okay, or 2 root GL, whatever. Okay. So let's look at an example based on this. So in next example, what we're doing is so a particle is attached to a light rod and it is given. Now the rod is taken to the vertical position with a particle on top. Okay. And the particle is given a horizontal velocity u, let's say, at the top. Okay. So length of the rod here is say 10 meters. Mass of the particle is 2 kilograms. G is 10 meters per second square. Now this initial speed given is 5 meters per second. So this is so first of all we will find the tension in the rod just after the motion is started at t equal to 0. Tension when the rod is horizontal. Tension at lowest point, and additionally we also have to find here the angular position of the rod at an instant when the tension is 0. So apparently there will be some instant when momentarily the tension will be zero in the rod. Okay, and you will understand that when you work out the first part of the question and compare it with, for example, the second or third part. See, as the particle is going through that vertical circular motion, at some point, just for an instant, the tension in the rod will be zero. So you have to find the angular position of that instant. Okay, so let's work out the answer for the first part. So if I assume, for example, that the tension is in this sort of direction, then I'll get tension as a negative quantity. Sorry, minus 1.5 m, no? So minus 3 newtons. Correct. Minus 30 newtons.
Yes, sir.
Wait, something has gone wrong here. This calculation, how much it is coming out to be?
So 7.5 into 2. Oh,
Yeah,
15.
yeah. So minus 15 newtons, yes.
Yes.
So the minus sign just shows that the direction of friction tension is opposite. So this basically means that the tension is equal to 15 newtons, but upwards at that point.
So why is it acting upwards?
Because there isn't enough velocity. Understanding? So the centrifugal force that is acting on the particle is not enough to exceed the weight. So the rod still has to support the particle.
Yes.
Tension has to be like this of 15 newtons. For example, if we had not given any speed and just tried to keep this thing in equilibrium, particle in equilibrium, we would have seen that the tension would have been 30 newtons. No?
Yes, sir.
It's become less than 30 newtons, but it's not become in the opposite direction. Okay, this is clear now?
Yes, sir.
Okay. Now see, from here, as the particle comes to the horizontal position, for example, now here the speed is supposed to become V1. So the tension has become T1. So you can see here that tension will be directly mv1 square by L. The horizontal position is the one where the tension is purely centripetal force. So at the horizontal position, so firstly you have V1 square is equal to U square plus 2GL from work energy, because the vertical displacement is L. Okay, so our V1 is becoming square root of the 25 plus 2 into 10 into 10. So 15 meters per second.
Yes.
So tension T1 will be mv1 square by L. That is, tension is equal to centripetal force and mg is equal to tangential force in this case. Okay, so T1 will simply become 225 into 5 by 10. Isn't it? So that's 225 by 2 or 102.5 newtons.
So the mass is 2 kgs.
Oh, sorry, the mass is 2 kgs. Okay. So then it is 225 by 5. So the tension is becoming how much now?
45.
45.
45 newtons. But now what is the direction of tension? Inwards. Okay. So you see, as the particle is transitioning from this vertical position to this horizontal position, the way the string is, the way the rod is behaving as far as force is concerned, tension is concerned, that is also transitioning. It is now like this. So in between somewhere, the tension must have been 0 for an instant.
Yes, sir.
Okay. From the vertical is highest to the horizontal position. Okay. The direction of tension transitions from radially outwards to radially inwards. Okay. So that is why you know that there will be some particular point where the tension will become 0 for an instant as it is transitioning. So that's how the last part of the question will make sense, and we can find out the angle at which that happens. So at some intermediate position in between, tension will be 0 at an instant or for an instant or whatever. Okay. So we'll come to that also. Now first find out the tension at the vertical position. When yeah, I said that's good. Okay. At the lowest position, let's find out the tension. Then we'll come to this also.
So 105.
Okay. Just check the value. What is the weight? The weight is 20 newtons. No?
Yes, sir.
So yeah, it will be more than 100 definitely. But less than 6 times the weight. Because the speed at the top that we have now, it is less than root GL. So the speed at the bottom is greater than root 4 GL, but less than root 5 GL. So like that, the tension will be greater than 5 times the weight, but less than 6 times. So actually, another way to analyze this question would have been that you look at this value of U at the top, which is 5 meters per second, and you compare the quantity root GL here, that is 10 meters per second. So you can see that U is equal to root GL by 2. So that is why you can see that the tension at the top will be upwards and not downwards. Had it been a thread, it would have been a slack thread at the top. It would not have developed any tension. The particle would have gone into a projectile motion. So V naught. So now coming to this third part, V naught will be equal to square root of U square plus 4GL. So that is root 17 by 2 GL. So that's another way of solving the question. You can also obviously solve it just numerically. That you know that U is 5 meters per second. So V naught is equal to 2GH like this. Okay, so just solve it numerically. Okay, now let's find that position at which the tension is becoming zero momentarily between the between the highest point and the horizontal point. So we can just take it as some angular position theta with respect to the initial starting point. Here the starting point is at the top. It's not at the bottom because that's how we started the motion. So you'll find it as an acute angle. If you reference it to the bottom point, of course, it will be obtuse angle, but here we need not do that. So here we can make note of this point that we are getting this tension negative at the top. The tension is upwards. Actually, that is happening because technically it's happening because U is less than root GL. Okay. The numerical limiting value of U for the tension to be downwards instead of upwards is that it should be greater than root GL. If we had projected it with a horizontal speed of exactly root GL, then momentarily the tension would have been zero at the top itself. Yes, very good, Abhinav. That's correct. Yes, very good. That's correct, Siddharth. Yeah, so if I'm solving this numerically, it will actually be better to start by, expressing U as in terms of GL. It will make the way of solving it much easier actually. But even if you don't do that, okay, so this is root GL by 2. So now let us say at some angular displacement theta, okay, the speed has become, instantaneous speed has become V. So V is equal to square root of U square plus 2GH, where this H will be L, 1 minus cos theta. So we have the first equation that V is equal to square root of 25 plus 2GL will become how much? 200, because L was 10, into 1 minus cos theta. We put it numerically, it will be like this. We put it parametrically. Yeah, we put it parametrically, it will be how much now? It will be GL, if we take common, it is square root of U square, which is 1 by 4 plus 2 into 1 minus cos theta, like this. That works. So anyway, we are going parametrically, we can use this. If we are going numerically, we can use this. Okay. Now the condition for tension to become 0 at this instant is that mg's centripetal component is equal to mv square by L. So T is equal to 0 implies that mg cos theta is equal to mv square by L. Parametrically, it is this equation, or numerically we substitute, it is 100 cos theta, this one. Okay, so we are solving parametrically, then considering this as our first condition and this as our second condition, solving equation 1 and 2, we can write V square as GL square root, sorry, root GL. So anyway, V square is GL into 1 by 4 plus 2 times 1 minus cos theta from this equation. And from the second equation, V square is GL cos theta. So ultimately, we are solving this equation 1 by 4 plus 2 minus 2 cos theta is equal to cos theta. Okay. Or if we are solving parametrically, we can say that P square from this above equation is 25 plus 200 into 1 minus cos theta. From the below equation, that is 100 cos theta. So two different ways of solving it. So 3 cos theta is 6/4. Sorry, I got this wrong. So I'll just minimize this a little. Okay, so cos inverse 0.75, let's check out. It will be probably less than 30. Sorry, something greater than 30, but less than 37. Not mistaken. It's about 41.4 degrees. Yes, 45 degrees is cos inverse 0.7 approximately. 37 degrees is cos inverse 0.6, 0.8, 4/5. So it's something in between these two. So makes sense. Okay, let's move on to the next question now. So last time we also discussed about instantaneous radius of curvature, okay, which is a more general principle in kinematics or generally mechanics. Okay. So let's look at an interesting question involving the concept of that thing. Okay. So in this question now we have Like let's say we have a metallic wire which we shaped like this. So we've shaped it like a parabolic curve. Like this, and we fixed it in the vertical XY plane. Okay. So here gravity is pointing along the negative y-axis. So this thing is a fixed metallic wire frame kind of thing. Okay. Along a curve, which is given by the equation y is equal to 3x square. Just make it simpler. Y is equal to 4x square. Where x is in meters, y is in meters. So it's shaped like this. Okay, now we have a ring that can slip without any friction acting on it. So that is initially at the point A, it is released from rest. Of mass, let us say 200 grams, can slip without friction. On the metallic wire frame. It is released u equal to 0 from the position, let's say x equal to 2, so y is equal to 16. So we have to find the ring's acceleration and the normal contact force between the ring and the frame. So both of these just after release at A and at the instant when the ring is at the lowest point O. So this is not a circular motion question, this is a totally different question. But in this you'll have to use general kinematics. Okay. So what is happening is that the ring's motion is constrained. It has to go along that wire frame. So it is constrained by the forces acting on it, which is a combination of contact force and weight, to move in such a way that it always moves along that path y is equal to 4x square. So accordingly, it has a fixed relationship, between tangential and centripetal or normal acceleration to keep it in that path. Okay, so it's while it's not a circular path, but at every point it has a defined instantaneous radius of curvature. Okay, so that's one thing. And the other thing you'll have to realize is how you make use of the dynamics. Okay, so just try this out. It's an interesting question. So this type of question is not very common at the JEE Advanced level. But it's within the syllabus because instantaneous radius of curvature is there in your syllabus. Okay. would be, for example, very common at INPHO level, or like that. Okay, so let's understand this question. Oops. Yeah. So to start with, let's find out the ring's acceleration and normal reaction when the motion starts. Okay, at that top position. So there it's basically just like a motion starting on an inclined surface, but we have to find the inclination, and that's where your calculus comes in. Rest, there is nothing else to that part. It's pretty simple. Another version of this also. Okay, so at this point of time, when the ring is here, so initial speed is 0, of course. Okay. So let's draw a tangent to this at this point. If the tangent is making an angle theta with a horizontal, tan theta is the value of dy by dx at the point E. Okay, so E is the point, was how much? First of all, the curve was what? Y is equal to 4x square, and E was the point, x is equal to 2, y is equal to 16, right? So anyway, so y is equal to 4x square, so dy by dx is 8x. So dy by dx at the point at the point E is equal to 8x at the point x equal to 2. Interestingly, tan theta is also equal to 16. So theta at that point is tan inverse 16, which will be quite a large angle. Okay. Anyway, so hope I've got all the values correct so far. Let's check. Yeah, y is equal to 4x square and E was the point. Okay. So technically, we won't really need to find out theta, okay, because we can, from this value, we can find out cos theta and sin theta. But anyway, so normal reaction will act in this direction, and mg will act in the vertically downward direction. So the particle at this moment will have only a tangential acceleration because its initial speed is 0. This angle is also theta. Oh, okay, okay. Okay, so Siddharth, you can go ahead. Problem. Just take the notes and the recording and send it later. Okay. So this is an internal exam you're having in school or something, or Okay, okay. Anybody else having a school exam right now at 9 o'clock?
No, sir.
Okay. All right. So anyway, coming back to this, so you can see that at this moment, n will be equal to mg cos theta. Okay. Why? Because the normal component of acceleration will be zero, because the initial speed is zero. So there is no normal acceleration. The normal acceleration in general at a point is equal to v square by r, where r is instantaneous radius of curvature. Whereas mg sine theta will be providing the tangential acceleration. So from this equation, you can see n will be equal to mg cos of that angle. So 0.2 into 10 into, now tan theta is equal to 16. So cos theta will become how much? 1 upon root 17, right?
So 257.
What?
So 16 square plus 1, right?
Oh, sorry. Yes, my mistake. 16 square plus 1. So 256 plus 1.
Yes, sir. 257.
247. So it is nearly 1 by 16 only.
So 257, right?
Yeah, so it's nearly 16 only, no? Root of 257. It's only marginally greater than that,
Yes, sir.
right? So n is approximately 2 by 16 or 1 by 8 or and the acceleration will be the purely tangential acceleration, which will be g sine theta. So the acceleration at that moment will be 10 into 16 by root 257. Okay. So this also, if you like, we can do a binomial approximation. 16 upon root 257, you can write as 16 upon 16 into 1 plus 1 by 256, right, to the power half. So that is 1 plus like this. It is nearly 1 by 500. Okay, now is the other part which is more interesting. Okay, so you'll see here that for the second part, we'll have to make use of the fact that normal reaction does not do work here. So mechanical energy is conserved. So if it's starting from rest at this point, by the time it comes to the lowest position, you can calculate the speed. This is from work energy theorem. So P at the lowest point. So that will be square root of 2 into 10 into 16 meters. So that is almost now 8 root 5 meters per second.
So how did we get 16?
Because the y coordinate was 16 na, at A. I remember the point A.
Yes, sir.
At a y coordinate of 16 and x coordinate of 2. Okay, so the diagram is actually a little bit misleading. The parabola is like this. So it's rising very steeply. The point A is more like something like this over here. Even more steep than this, okay. So here the speed is 0, whereas by the time it comes to the bottommost point, it got the maximum speed actually, okay, and that speed is this much. Okay. All right, now what is happening at the bottommost point in terms of dynamics? There is mg acting downwards and normal reaction acting like this, and it has an instantaneous curvature like this. No? So if that curvature is of radius r, so at the point O, what is happening? N minus mg should be equal to this, okay? And tangential acceleration for an instant will be 0, because at that instant, dv by dt is 0, because v has reached its maxima. Up to the point O, v is increasing, so tangential acceleration is positive. And as it crosses the point O, tangential acceleration becomes negative. So momentarily, tangential acceleration is 0. Also, you can see there's no tangential force. So dynamically also, okay. So now to find n, we have to find the normal acceleration. Now the normal acceleration will be how much? It will be v square by r. Now this is where v we have already found out about, okay. But r we have to find out using what? The geometry of the problem, okay. Using that second derivative of that method, remember? Instantaneous radius of curvature formula.
Yes,
okay. So what was the formula for the instantaneous radius of curvature?
so 1 plus dy by dx, the whole
Whole square.
square
Uh,
to the
what
power
is
3
the
by
power
2
3 by 2? Yes.
by second derivative.
Divided by mod of second derivative. Yes. Okay. So for this, we have to use that formula that for a curve or a trajectory, y is equal to fx in the xy plane. Instantaneous radius of curvature is easy way to write this formula. So here we have to just do that whole calculation now for this particular trajectory, which is y is equal to 4x square. So we have to find this term, okay, and then substitute the value of this term at the origin. So the origin is the point where x and y coordinate are both 0. So that will give us both the things, the acceleration as well as the normal reaction. Okay, so let's do that now. So y is equal to 4x square. So dy by dx is 8x, okay, and d2y by dx square is 8. So instantaneous radius of curvature at any point becomes instantaneous radius of curvature at 0 becomes the value of this expression at x equal to 0, y equal to 0, which is 1 by 8. .5 centimeters. That is the instantaneous radius of curvature at the origin. So now you can understand that as that particle is passing through that lowest point, it will have a normal acceleration and a tangential acceleration of 0. So the V we have found out from work energy. H was the height it started from. And R we have found out as the value of instantaneous radius of curvature at the origin, which is 0.125 meters. So the normal acceleration is becoming 320, 64 into 5 divided by 0.125. It's a pretty incredible amount of acceleration because it's going through a very sharp turn actually. If you really visualize the problem, with a proper drawing to scale, you'll understand that as it passes through that origin, going through a very, very sharp turn. And it's going at a pretty large amount of speed because you've started the particle from a pretty high position. You started it from somewhere here. So by the time it's coming here, it has a pretty large amount of velocity. And because it's a sharp curve like that, so it has a small radius of curvature at that point. It's going through a sharp corner. So it has a tremendous amount of acceleration. So that will create a tremendous amount of normal reaction between the two. So practically what will happen is at such a large value of normal reaction, you cannot really ignore friction, because even if the coefficient of friction is very, very small, so generally speaking, we would ignore friction, but here the normal reaction would become tremendously high. So this question is like, not going to be easy to replicate practically, because while you can design a curved path like that and all that, okay, but the friction would become significant at such large values of normal reaction.
Sir, is there any chance of the ring breaking or something?
Yeah, it can happen because normal reaction being such a large amount of force will, it will create high stress on the material of the ring as well as the material of the wire.
So it'll get bent.
It can get bent, it can actually split. Okay. Number of things can happen. Okay.
Okay, sir.
So this is how much? 320 divided by 0.125. Yeah, it's a pretty large amount of acceleration. Okay.
So this is a INPHO level question.
Yeah, in concept, you can say yes, because this instantaneous radius of curvature is a pretty normal thing at IITJEE level, but at JEE Advanced level, very few questions over the years have been based on instantaneous radius of curvature.
Okay, sir.
In that sense, there's nothing very difficult about the question, but it's just that this concept is generally not asked that much at JEE Advanced level.
Yes, sir. Even
At JEE level even. Yeah. So if you know the concept of radius of curvature, you can see there's not too much to it. You're just applying conservation of energy and that second derivative and all that to find the instantaneous radius of curvature. Now, once you found this normal reaction, now you go back to that equation and you can see, this normal acceleration. Okay, you can see that n will be equal to mg plus this. Okay, so from that you can find the value of n. Okay, and your net acceleration only at the origin will be equal to this normal acceleration because the tangential acceleration will be 0. Okay.
Yes, sir.
Okay. Now, at a practical level, perhaps, if we had taken the question such that instead of y is equal to 4x square, y was equal to x square by 4 or something, we would have got a smoother type of parabola like this. So the curvature would have been less steep, so the radius would have been larger. So you would have got more practical kind of values for acceleration, comparable to acceleration due to gravity, not so very large. Okay.
Yes,
But
sir.
anyway, I mean, if you really think about the practical aspect of this question, the particle is falling through a vertical height of 16 meters along such a narrow curve. So it will pick up, quite a bit of speed, and then it's going through a very sharp corner. So something pretty extreme is happening dynamically to it. So that's why we are getting those kind of extreme results. Okay. All
Okay,
right.
sir.
Now back to circular motion. Now this type of question, which I'm going to discuss next, is pretty common at JEE level. Okay. So this will now include one more thing in our analysis of vertical circular motion. So again, this is a fixed ring which is in the vertical plane. Okay. So imagine somehow we have attached a ring like this, a metallic ring like this, to a vertical plane, but such that it's continuous. There's no break at any point. So this is a fixed metallic frame. So it's like a metal wire in a circular shape. Circular shape of radius something, let's say 5 meters. Okay. Now what we have here is that attached to the top point of the ring is a spring. Okay. And the other end of the spring is attached to a ring. Okay, so this point is a fixed point. Okay, where the spring is attached at the top. Of that fixed metallic frame. Is all in a vertical plane. So G is like this. Okay, and the other end is attached to, this is a ring of mass m equal to something, let's say 2 kgs. Okay. And this particular spring has a spring constant K. Now this ring starts, we release it from this position A, where this angle is 60 degrees. And when we release it at A with an initial speed of 0, the spring is also having 0 extension. It's at natural length. That is the situation. Now what we observe is that on releasing it, the ring first accelerates and then decelerates. And by the time it reaches the lowest position B here, it momentarily comes to rest. Okay. So the ring is released from rest at the position A and can slip freely. There is no friction. On the metal frame. The spring is attached at one end to the fixed point T at the top of the frame, and at the other end the ring. At A, that is the initial state, the spring is in relaxed state. Now, it is observed that the ring comes to rest at D, that is the lowest point. So find the value of the spring constant in Newton per meter. Okay, because the mass of the ring is given to you, acceleration due to gravity is given to you and all that. Okay. And also if this position here is C, then we also want to find the speed and acceleration of the ring when it is at C. So we'll start with these two things. We'll discuss one more thing in this problem, and that is about the normal contact force between the ring and the particle, or the ring and the wire frame. Okay, but start with these two problems. I mean, these two aspects. Okay. So hope the question is clear.
Yes, sir.
This is very similar to a very well-known subjective question that had come in JEE, IIT-JEE long back. I mean, the position of the ring and all that was different in that, but the concept used is exactly the same. So this is important from JEE point of view. Okay, so people, what is the concept we'll use to find the spring constant?
So we'll just equate the forces at B.
No. Forces equate करके क्या होगा बेटा? Forces equate करने से तो acceleration is 0 ना? But what is the condition at the point B?
Yes, that the spring force is equal to mg.
Why can't there be contact force? It's a ring, na?
Yes,
What's the
sir.
point now? Yes, acceleration will be 0 at B because momentarily it comes to rest. Okay. So centripetal is also 0 and there's no tangential force geometrically. Okay. But the thing is that is not going to give us the value of K, na?
So we
No,
are going
sir.
to
So
conserve
what you have to
the
focus in is
work
why
done.
V 0. Yeah, better tell.
So we are going to conserve the work done by the process.
Yes, very good.
MGH
We have to
and
conserve energy. Huh? Or you can use work energy theorem. That going from A to B, what is happening? Gravity is doing positive work and the spring is ending up doing some negative work. So the net work done should be 0. But both are conservative forces, so you can make use of potential energy concept, right?
Yes, sir.
Understood, huh? So again, it is that trick that normal contact force is not doing any work and there's no non-conservative force. So we can make use of work energy. There's a sort of checks and balances thing that is happening in terms of work energy. The amount of positive work done by gravity, or another way of saying it is the loss in gravitational potential energy, is exactly equal to the work done by the spring force. Okay. Negative work done by spring force, or the gain in spring potential energy, elastic potential energy of the spring. So as you're going from this position to this position, because the spring is storing so much potential energy, there's no kinetic energy left at B. So it's a very simple thing actually. At B, speed is 0. So therefore it implies that A to B, the change in gravitational potential energy plus the change in potential energy of the spring should be 0. Because this means that change in kinetic energy is 0. So the combination of kinetic energy plus gravitational potential energy plus elastic potential energy of the spring is conserved. Why? Because work done by normal reaction is 0 and there is no non-conservative force here like friction. Okay, so now all we have to do is we have to find the extension of the spring at this stage. It has some natural length plus x and the natural length is this. That's pretty easy. This is an equilateral triangle. So you can see that the natural length for the spring is equal to r and
Yes,
therefore
sir.
L plus x is 2r. So the extension is r. So here to here, this is the height. R sine 30 plus r by 2 . So our K is equal to mg into h divided by or 2 times mg divided by x square, correct?
Yes, sir.
So 2 times what was the mass 2 kgs now?
Yes, sir.
To r was how much? 5 meters. So I'm getting 12 Newton per meter. Just check the solution, but solving.
Yes, that's correct.
Okay. So That was one thing. Now, next we have to do the analysis at the point B. Okay, what is the, so next part actually, let's do a couple of things. Let's calculate spring force, normal contact force, speed and acceleration, all these things at the point C. So whatever I have given earlier, just add to that we have to also find the spring force and the normal contact force at the point C. Same way, if you want to do the analysis of forces at B, you can also look at that when the particle is at that point B, or when the ring is at that point B, as far as forces are concerned, there is spring force, there is mg, and there will also be some kind of normal contact force, which will be like this. Because at this point, its acceleration has become 0, its speed has become 0. So you'll have n is equal to kx minus mg. Kx is 60, 12 into 5, and mg is 20. So there'll be a normal contact force of 40 newtons. But that is at the position B. Now we have to repeat all this for C. So once again, you have to use work energy, one relation. You have to use dynamics, another relation. And you have to use spring. You have to use geometry to understand the extension of the spring.
So dynamics, geometry, sir, other one was?
Work energy.
Okay, sir.
Because you need centripetal acceleration, you need speed, all these things. Now, by the time it reaches the point C, the spring has become like this. So the spring has become, has an extension like this. The particle has a speed v like this, and therefore it has a combination of centripetal acceleration and tangential acceleration. So when we look at the free body diagram of the particle, or the ring rather, it has mg acting vertically downwards. It has a spring force which will act at
45
45 degrees like this. And most likely it will have a normal contact force which might be acting like this. But it might become negative, in which case it's inwards. It all depends on the relationship between speed and spring force and all that. Your centripetal acceleration and spring force. So first thing, E to C, apply conservation of energy. But before that, let's also find X of the spring. At the point C, what is the value of X? So let's look at that. L was equal to R, okay. And
Yes, sir.
L plus X is R root 2. Okay, so X is, so we'll take root 2 as 1.4, okay, for simplicity. So 0.4 R, so that is 2 meters, okay. That is our X. And we calculated K earlier, it was 12 Newton per meter, right?
Yes, sir.
So conservation of energy will tell us what, that plus half mv square, speed is increasing, okay, minus mgh plus half kx square should be 0, where h is now this height. So h is simply r by 2, right? So v square is equal to 2gh minus k by m x square. So 2 into 10 into 5 by 2 minus k was 12, m was 2, into x is how much now? X is 2 meters, right? So 2 square. Getting v as square root of 50 minus 24. So root 26 meters per second. So root 26 approximately 5.1. So now I know that centripetal acceleration v square by r be 26 by 5 or 5.2 meters per second square. Okay. So from that I know, coming to the free body diagram, that kx cos 45 minus n according to my direction of this is equal to mass into centripetal acceleration. So kx is 12 into 2 minus n should be equal to 2 into 5.2, and I will take root 2 as 1.4, so I'll take 1 by root 2 as 0.7 using the same approximation. So n according to me should become 24 into 0.7. That's how much? 16.8, no?
Yes, sir.
minus 10.4. Yeah, so I have guessed the direction of normal reaction correctly. It's positive, so it's outwards only. So the spring force is so much now that it's making the particle sort of pull inwards against this. So anyway, so this is coming out to be that now 6.2 newtons. And
6.4.
6.4. And what about the tangential acceleration? It will be equal to G, because there's only one tangential force, mg. Oh no, sorry, there's kx sine 45 upwards, you know.
Yes, sir.
Okay, so we'll have to take that into account. Okay, so this is normal reaction that is done. Okay, speed we have got. This was one of the answers. Now we also need to find acceleration. So for acceleration, we've already got centripetal acceleration, but we need tangential acceleration. So for the tangential acceleration along the tangential direction, we can see the analysis that mg minus kx sine 45, that is equal to mass into tangential acceleration.
Yes, sir.
Okay, so 20 minus 12 into 2 into 0.7 again is equal to 2 times tangential acceleration. So 20 minus 16.8. So my tangential acceleration is coming out to be how much?
1.6.
3.2 divided. So 1.6 meters per second square. So that will now tell me that my net acceleration is okay. So this question is clear, I hope.
Yes, sir.
Yes, sir.
Okay, right. So with this we now complete circular motion. Okay, so please this week try to concentrate on completing all questions.
Excuse me,
from
sir.
the-
I had one other doubt in circular motion, sir. I sent you on WhatsApp. Could you please check that question as well?
Yeah. This one, level 2, question number 2. That the one?
Yes, sir.
Okay, so in this question now, whether the equilibrium is stable or unstable now. So to check that now, what you do is you first find the equilibrium position. It's a smooth surface now.
Yes, and omega is also constant.
Omega is constant, but the position, the surface is smooth now. Okay, so at equilibrium position, what you can see now, centrifugal forces sine component will cancel, rather centrifugal forces cos component will cancel mg sine component, right?
Yes, sir.
Now, if you take it above the equilibrium position, what happens to centrifugal force? It increases because your R has become larger, na? Omega is same.
Yes, sir. It increased.
Okay, so what is happening? The force taking it up the inclined plane is increasing, na? Compared to mg sine theta down the inclined plane.
Yes, sir.
So it's a non-restorative force, na? It takes it further up.
So the equilibrium will be unstable
Huh?
then.
Similarly, if you
Yes.
take it below the equilibrium position, mg sine theta is remaining the same, but your centrifugal force's cos component is decreasing, na?
So again, non-restorative.
So on either side of equilibrium, you have what is called a non-restorative force. A force which is, instead of restoring it, is taking it further away from equilibrium. Okay, na?
Yes, sir. Yes.
So it is an unstable equilibrium force. Okay, people, we will conclude today's session. Okay, and we have another session this week. So we will start center of mass in that session. Okay. We will keep time for doubts and all that, but probably we'll keep that in the next week so that you can complete all the module questions and all that. Okay. I'll send you a revision exercise in circular motion also. But first target, please complete the module of circular motion.
Okay,
So that's
sir.
it for today's class, people. Yes. Wish you all the best.
Thank
Have
you,
a nice
Bye, sir.
day. Bye.
Thank you, sir.
Thank you,
Bye,
sir.
sir.
Bye, sir.
Thank you, sir. Bye, sir.
Bye, people. Bye.